Quantum physics can seem strange and counterintuitive. It governs the microscopic world of atoms and subatomic particles. At this scale, the rules of classical physics break down. In the quantum realm, energy and matter behave in unexpected ways. Quantum physics helps us understand the nature of reality at its most fundamental level. Imagine a world where particles can be in multiple places at once. Picture a reality where matter can tunnel through seemingly impenetrable barriers. This is the captivating realm of quantum physics. Quantum physics has led to groundbreaking discoveries. It has given us lasers, transistors, and magnetic resonance imaging, or MRI. Today, quantum physics is paving the way for quantum computers. These computers have the potential to revolutionize fields like medicine, materials, science, and artificial intelligence. Quantum computing harnesses the principles of quantum mechanics to process information in ways classical computers cannot. In cryptography, quantum physics ensures secure communication through quantum key distribution. Medical imaging technologies like MRI rely on quantum principles to provide detailed images of the human body. These real-world applications showcase the transformative power of quantum physics in our everyday lives.
In the early 20th century, a physicist named Louis de Broglie proposed a groundbreaking idea. He suggested that all matter, not just light, can exhibit wave-like properties. This revolutionary concept is known as de Broglie's hypothesis. De Broglie's hypothesis states that every particle has an associated wavelength. This wavelength is inversely proportional to the particle's momentum. A particle with higher momentum has a shorter wavelength, and vice versa. This relationship is described by the de Broglie wavelength equation, lambda equals h over p. In this equation, lambda represents the de Broglie wavelength, h is Planck's constant, and p is the momentum of the particle. Planck's constant is a fundamental constant in quantum mechanics.
Matter waves exhibit fascinating properties that defy classical intuition. One of the most striking properties is their ability to interfere and diffract. Imagine two waves meeting on the surface of a pond. When the crests of the waves align, they reinforce each other, creating a larger wave. When a crest meets a trough, they cancel each other out. This phenomenon is called interference. Matter waves can also bend around obstacles, just like water waves bending around a rock. This phenomenon is called diffraction. The diffraction of matter waves was experimentally confirmed in the Davison-Germer experiment. In this experiment, electrons were fired at a nickel crystal. The scattered electrons formed a diffraction pattern, providing evidence for the wave nature of matter.
In quantum mechanics, the wave function is a mathematical function that describes the quantum state of a particle or system. It is represented by the Greek letter psi. The wave function contains all the information we can possibly know about a quantum system. The wave function itself is not directly observable. However, its squared magnitude gives us the probability density of finding the particle at a particular point in space and time. The probability density tells us the likelihood of finding the particle in a specific region. The wave function is a complex valued function. This means that it has both a real part and an imaginary part. The imaginary part of the wave function is crucial for describing interference and other wave-like phenomena.
De Broglie wavelength in action. The de Broglie wavelength has profound implications for our understanding of matter. It bridges the gap between classical and quantum physics, offering a new perspective on the behavior of particles at the atomic and subatomic levels. It explains why atoms are stable and why electrons in atoms occupy specific energy levels. This concept is crucial for understanding the structure of the periodic table and the chemical properties of elements. Consider the electron in a hydrogen atom. This simple system provides a clear example of how the de Broglie wavelength operates. The electron is bound to the nucleus by the electromagnetic force. This force is what keeps the electron in orbit around the nucleus, much like how gravity keeps planets in orbit around the sun. According to classical physics, the electron should continuously emit radiation as it orbits the nucleus. This radiation would cause the electron to lose energy over time. This would cause the electron to lose energy and spiral into the nucleus, making the atom unstable. If this were true, atoms as we know them could not exist. However, the de Broglie wavelength provides an explanation for the stability of atoms. It introduces the concept of wave-particle duality, where particles like electrons exhibit both wave-like and particle-like properties. The electron's wave-like nature confines it to specific orbits around the nucleus. These orbits are not arbitrary but are determined by the electron's wavelength. These orbits correspond to specific energy levels. Each energy level is associated with a particular wavelength, and the electron can only occupy these discrete levels. The electron can only exist in these allowed energy levels, preventing it from spiraling into the nucleus. This quantization of energy levels is a fundamental principle of quantum mechanics and is essential for the stability of matter.
Schrödinger's equation, the quantum compass. Schrödinger's equation is a fundamental equation in quantum mechanics. It is a mathematical equation that describes how the wave function of a quantum system evolves over time. This equation was developed by Austrian physicist Erwin Schrödinger in 1926. The time-dependent Schrödinger equation is a partial differential equation. It relates the time derivative of the wave function to the Hamiltonian operator acting on the wave function. The Hamiltonian operator represents the total energy of the system. The time-independent Schrödinger equation is a special case of the time-dependent equation. It applies to systems where the potential energy does not depend on time. This equation is used to find the stationary states of a quantum system, which are states with a well-defined energy.
Quantum tunneling leaping through walls. Quantum tunneling is a fascinating phenomenon in which a particle can pass through a potential barrier even if its energy is lower than the potential energy of the barrier. This seemingly impossible feat is a cornerstone of quantum mechanics, a field that continues to baffle and intrigue scientists. This is a purely quantum mechanical effect that has no counterpart in classical physics. In the classical world, objects need sufficient energy to overcome barriers, but quantum mechanics defies this intuitive understanding. Imagine rolling a ball up a hill. In our everyday experience, if the ball doesn't have enough energy to reach the top of the hill, it will roll back down. This is a simple demonstration of classical physics. However, in the quantum world, things work differently. There is a small yet significant probability that the ball could tunnel through the hill and appear on the other side as if by magic. This phenomenon, while strange, is not just a theoretical curiosity. Quantum tunneling is crucial for many physical processes, including nuclear fusion in stars, where it allows particles to overcome repulsive forces and fuse together, releasing vast amounts of energy. It also plays a vital role in the operation of transistors in electronic devices, which are the building blocks of modern technology. Without quantum tunneling, the miniaturization of electronic components would not be possible. Additionally, quantum tunneling is the basis for scanning tunneling microscopy, a technique that allows us to image surfaces at the atomic scale. This has revolutionized our ability to study and manipulate materials at the smallest scales, opening up new frontiers in nanotechnology and materials science.
Quantum computing. The future is now. Quantum computing is a new paradigm of computing that harnesses the principles of quantum mechanics to solve problems that are intractable for classical computers. This revolutionary technology has the potential to transform industries, from cryptography to pharmaceuticals, by providing unprecedented computational power. Unlike classical computers, which store information as bits, zeros or ones, quantum computers use qubits. These qubits are the fundamental units of quantum information, and they operate in ways that defy our traditional understanding of computing. A qubit can exist in a superposition of states, meaning that it can be in both the 0 and 1 states simultaneously. This unique property allows quantum computers to process a vast amount of information at once, making them incredibly powerful for specific tasks. This allows quantum computers to perform operations on multiple possible values at the same time, giving them a significant speed advantage for certain types of problems. For example, they can solve complex optimization problems and simulate molecular structures much faster than classical computers. Another key concept in quantum computing is entanglement. This phenomenon is one of the most intriguing aspects of quantum mechanics and is essential for the power of quantum computers. Entanglement is a special correlation between two or more qubits. When qubits are entangled, their states become interconnected, such that the state of one qubit directly influences the state of another, no matter the distance between them. When qubits are entangled, they are linked together in a way that cannot be described by classical physics. This entanglement enables quantum computers to perform complex calculations with a level of efficiency and speed that is unattainable by classical computers, opening up new possibilities for technological advancements and scientific discoveries.
Quantum ethics, navigating the unknown. As quantum technologies advance, it's crucial to consider the ethical implications. Quantum computers have the potential to break current encryption algorithms, posing risks to data security and privacy. The development of quantum technologies raises concerns about job displacement. Quantum computers could automate tasks currently performed by humans, potentially leading to economic inequality. The accessibility of quantum technologies is another ethical consideration. It's important to ensure that the benefits of quantum technologies are distributed equitably and that they don't exacerbate existing social divides.